let me go back to the case of the IID random variables. So we proved that if you take a closed set F, take the log, you divide that by n, you take the limit sup. We proved that this was bounded by, well, we had here beta theta minus log of m theta. And so here we had a supremum over beta in F, infimum over theta in R, and minus. So this is what we proved. And of course it's here it's an infimum. And here's a sup. Okay, so first observation is that, and so what I want to discuss is how to invert this sup with this imp. So my first observation is that we never use that f is closed in this argument. Okay? We are using here to exchange, but before, up to this point in which we had this inequality, we never used that. Okay? This could be proven for any set F. So I want to show you how to get the bound we want, which is the minus infimum beta in F, sup in theta of beta t minus log m. So this is what we want to prove. So I want to show you how to obtain this in the case in which f is compact. Well, in our case here, in which we are considering Bernoulli random variables, since the space is compact, closed and compact are the same, so here it's fine, but in generality, the argument I will give you applies only to compact sets. And then, once you know it for compact, well, you have a closed set, you take an intersection with a compact set, and you have to show that the probability that you will be out of this compact set is very small. So there is an extra argument, technical argument, that you need to show that you can restrict to compact sets. Okay? And this piece I won't show. And instead of writing this expression in this way, let me write it with the minus sign inside. So what we have is that the infimum of theta in R, supremum of beta in F, of minus, so, and this function I will call it g theta beta. Okay, where g theta beta, it's now so minus beta t plus log of mt. Okay, and what I will need is that this function is upper semi-continuous, but we'll see that in a while. So I want to prove this inequality, but with the minus sign inside, because that will help my, okay, so the argument is simpler if I do that. So the first observation is that take f, and I will assume that f is bounded by union, finite union. And so what I can prove is that this limit sup of 1 over n log the probability that xn bar belongs to f. This is what I want to bound. Well, since f is bounded by f is contained in this set, this is bounded by the probability that xn bar belongs to this union. This probability is bounded by the sum of the probabilities. So this is bounded by the limit sup of 1 over n log of the sum of probability that xn bar belongs to aj. Now we have seen that if I have the limit sup of 1 over n of log of a finite sum, this is bounded by the maximum of the limit sups. So do you remember that? Okay, we have a sum, and we proved that if I have 1 over n log of a sum, finite sum, then the limit sup is bounded by the maximums of. We have seen that. Now, for this expression, I can just recall the bound I had. Okay. But so I'm using this formulation. So this is bounded by the maximum of now the infimum the supremum of this function. Okay, so this is what we can prove with the argument I presented yesterday. And this holds for any sets aj such that the finite union contains f. So I can minimize over all these finite unions. So here I minimize, and I will take these sets aj open. So here I'm minimizing over all finite open covering of my set F. Okay. So the argument I presented yesterday gives you this bound. And now I want to prove that this expression is bounded by the one I want, which is this version. But with the minus inside, so this is bounded by the supremum of beta in F, the infimum of theta of j theta beta. Okay? So if I can prove this bound, then I have indeed the inequality which I'm seeking. Okay, so this is the inequality I want to prove. And this argument is due to Varad, and it's really beautiful. So I will call this L. Okay? If L is infinite, there is nothing to prove. So I can assume that L is finite, so that this supremum is finite. So I'll call this supremum L, which is finite, and fix epsilon positive. Okay? So, since this is a supremum, if you fix a beta, this infimum is bounded by L. Okay? So, for all beta in F, we have that the infimum in theta of j theta beta, that this is bounded by L. Okay. Whatever beta, this infimum is bounded by L. Right? Now, so I need now this function. So this is the assumption I'll make, that for each beta, I need this function to be upper semi-continuous. Okay. Remember that, okay, in our case, this is clearly because everything is continuous, so it's clearly upper semi-continuous. Okay, but in this argument, I will need this function to be upper semi-continuous. Okay. So here, this one is differentiable, so there is no problem. So if this function is upper semi-continuous, so this infimum, it's bounded, it's less or equal than L. So with that fixed epsilon, this means that I can find some theta for which this j theta beta will be bounded by L plus epsilon. Right? Since this infimum is bounded by L, so I know that there exists a theta which depends on beta, such that j of theta beta beta, it's bounded by L plus epsilon. All right? Now, I fix, and sorry, here upper semi-continuous, the other variable. I'll use that. This one is. So sorry, here I said it wrongly. What I want to do is I want to assume that for each fixed theta, this function is upper semi-continuous. So it's upper semi-continuous in the other variable. Which there, well, it's linear, so it's fine. So since at theta beta, so now I fix theta beta, I know that this is bounded by L minus plus epsilon. So since this function, it's upper semi-continuous, this means that I can find a neighborhood for which this is bounded by L plus 2 epsilon. So let me remind you, if you take, just to fix ideas, if you want a lower semi-continuous function, it's a supremum of continuous functions. So let's say that you take these functions converging, so what's at the end, what you get, it's something like that. While an upper semi-continuous, so these are supremum. So supremum of continuous functions are lower semi-continuous, while infimum of continuous functions are upper semi-continuous. So now if you take the infimum, what you get, it's exactly a different picture. So for upper semi-continuous function, if you fix a point, you take the value of this point, you take an epsilon, and then you can find the neighborhood of this point at which all the function is bounded by the value here plus an epsilon. So you see here, if I take, well, this is the problematic point. If I take the value of this point, I add epsilon, then I can find a neighborhood at which the function is still bounded by this value plus epsilon. That won't be true for such a function, a lower semi-continuous function, because for the lower semi-continuous function, if you take this point, well, you have here, you can't find this neighborhood, okay? But for upper semi-continuous function, this is true. And this is why I'm assuming that this function is upper semi-continuous. So since at this value, it is bounded by L plus epsilon, I can find a neighborhood of beta for which this is still true. Okay, so there exists a neighborhood of beta. So let me call it n beta. So n beta, it's an open set which contains beta, for which so this is true for all points in n beta. So the supremum for gamma in n beta is such that this is true. Okay? So for each beta in F, we constructed a neighborhood, n beta, for which this inequality holds. Right? Now, fine. But since now I want to take the infimum, if this is true, if I take the infimum over all theta in R, it's still true that the supremum for gamma in n beta of j theta gamma, that this is bounded by L plus 2 epsilon. Because it's true for theta beta. So if I take the infimum over all theta, it's, of course, true. Okay? Okay, and now this is true. Okay. Now, what do I, so here I will use the compactness of my set F. What I did up to now is that for each beta in F, I constructed a neighborhood n beta right, for which, so n beta, it's a neighborhood, so it's an open set which contains beta. So this family n beta, for beta in F, it's an open covering of my set F. And since F is compact, it has a finite open covering. So I have eta beta 1, eta beta k, which are such that F is contained in this. Okay, so from this covering, I can extract a finite open covering because the set is compact, and it's here where I'm using the fact that the set is compact. Well, and this inequality holds for all of these points. This is true for all of these neighborhoods, right? So it's also true if I take here n beta j. Okay, remember what we proved is that for all beta in F, I had this inequality. So now let's take these particular betas, which are beta 1 up to beta k. Okay, so this is also true for all these beta j, for j between 1 and k. So what I get is that, well, since this is true for j equal 1 up to k, it's also true if I take the maximum Fine? So what happened? Well, I constructed an open covering of my finite open covering of my set F, for which the maximum over all elements of this covering, the infimum, the supremum of this, is bounded by L plus 2 epsilon. Well, this means that if I take the infimum over all finite open covering of my set F, then the infimum of the max as the infimum of the sup, it's bounded by L plus 2 epsilon, because I constructed one. So this proves exactly that this expression here on the left-hand side is bounded by L plus 2 epsilon. Well, but epsilon it's anything, so I send epsilon to 0 to get this inequality. Okay? So this is how you prove the bound you were looking for in the case in which F is a compact set. Okay, so this is an argument in order to get this inequality by using what we did yesterday. But you can also look in the literature and you will find conditions on this function j theta beta for which you can invert this inf with the sup. These are called the inf-sup theorems, and essentially you need, as I said yesterday, j to be convex on one variable and concave on the other. So there are general theorems which allow you to exchange, so you can look for them. But this is a simple argument, brilliant argument, to get what you need in the case in which F is a compact set. Okay, questions about this argument? So this gives you the upper bound in the when the set is compact, and so to get the upper bound, so for closed sets, what you'll need to do is you want an upper bound for that, so you'll write this as F intersection compact set, let's say P. Okay, you construct a family of compact sets, Kp. So now again, you take the log and you divide by n and you take the limit sup. And so you'll show with this inequality that this is bounded by the maximum. For the first term, this is a compact set. So you have your bound, which is, well, minus the infimum in beta belonging to F intersection Kp of I of beta. And here you have this limit sup. So 1 over n log the probability that xn bar belongs to the complement of this compact set. So this will give you a sequence gamma p. Okay. So if you are able to construct a sequence of compact sets for which this is converging to minus infinity, then you send p to infinity, you have here the maximum. The maximum will be this term in which Kp, you're taking p to infinity. Okay? So what I'm saying is that this infimum, since you're taking this infimum in a smaller set, this infimum is larger than the infimum of beta in F, of I beta, right? If I compare the infimum with the infimum, since you're taking here an infimum in a smaller set, this infimum is larger than this one, but with a minus sign, this is larger or equal. So you get that. So the only point is to find this sequence of compact sets. Okay? So in order to go from upper bound of compact sets to closed sets, what you need to do is to find this family of compact sets with this property, that this is bounded by gamma p, and gamma p converges to minus infinity. So questions about that? Okay. So that's one point, one observation. No questions? Okay. So the second observation is that in order to prove the upper and the lower bound, well, what we did is we introduced an object which was an exponential. So let's say for the upper bound, which was Sn minus n log of m theta. Okay. So this expression here appeared. So let me call that Mn. And my observation, so you remember that we introduced that expression in order to get the upper and the lower bound, right? And this was exactly the Radon-Nikodym derivative of a measure with respect to another. So we have here a family. For each theta, we had, okay, and I forgot theta here, right? Theta is n minus log n times log m theta. Okay? So for each theta, we had these, well, we have here a sequence of random variables. So we introduce this sequence of random variables, and my claim is, and this is important, that actually this sequence of random variables is a martingale. So my observation is that actually Mn, it's a martingale which is positive and has expectation equal to 1. And it's a martingale with respect to which filtration, well, in this case, the filtration is the one generated by x1, xn. So it's clear by definition that Mn is indeed measurable with respect to this filtration. So let's show that the martingale property holds. That if I take the expectation of Mn plus 1 given Fn, that this is equal to Mn. So let's compute the conditional expectation. So this is, by definition, the theta. So what is Sn plus 1? It's the sum of xj now you see that, well, this is a constant, and all these variables are Fn measurable, but the last one. So this is equal to the expectation, the exponential of theta Sn minus n plus 1 log of m theta, and the expectation of exponential theta xn plus 1 given Fn. Right? But this is, these variables are IID. So when I'm taking the conditional expectation, this is the expectation. So this is the expectation of exponential theta xn plus 1. But these random variables are IID. And so this is exactly what we called m of theta. Okay? And so you see that I can rewrite this at the exponential of log of m theta. And this exponential log m theta will cancel this plus 1, and therefore this is exactly equal to mn. So indeed, this sequence, it's a sequence of it's a martingale. So the sequence we introduced, the perturbation, so remember these are Radon-Nikodym derivatives, these are the perturbations we introduced, these perturbations form martingales. Right? And so this is very important. In the context of a Markov process, we will also perturb our measure by positive martingales, mean one positive martingales. And then a natural question is, well, what are the martingales in the context of Markov chains, continuous time Markov chains? And so let's fix our state space E, our continuous time Markov chain X, and we ask, well, what are the exponential martingales? Okay. We have seen that fxt minus 0t lf xs ds, that this is a martingale. But these martingales are not exponential, are not positive. So my claim is the following. Well, you take any function f in E to R, then you take the exponential of fxt minus fx0 minus the integral from 0 to t of exponential minus fxs, L of exponential f xs ds, that this is a martingale. So here are the exponential martingales. For each function f, this gives me a martingale. This martingale, it's positive because it's the exponential, and if it's a martingale, you see that at time 0, everything cancels. So at time 0, this martingale, it's 1, and therefore the expectation of this martingale, it's constant equal to 1. Okay, so let's prove that this is a martingale. So what I need to do is compute this conditional expectation. Okay? And I want to show that this is equal to MT. So let's compute that using the Markov property. So I have here fxt minus fx0 minus the integral 0 to t. Let me call that v. And here I'm computing at time t plus s. So fx0, it's measurable, and the piece of the integral which goes from 0 to t, it's measurable. So it gets out. So this is equal to the exponential minus fx0 minus the integral from 0 to t f, okay, we put r, fxr dr. And then what remains, it's fxt plus s, and this integral from t to t plus s. So here I use the Markov property to say that this is equal to the expectation starting from xt of the exponential of fxs minus the integral from 0 to s of v xr dr. Right, so here I have fxt plus s, and here the integral from t to t plus s. So everything starts from t. So I use just the Markov property saying that, well, this is start a new chain at xt and look at what happens from time 0 to s. Right? Fine. Mind that if s is equal to 0, this is exponential fxt. And if I get that this is exponential fxt, this is exactly what I get here. With fxt here, this is the martingale at time t. So I have to prove that this expression is equal to exponential fxt. In other words, what I need to prove is that the expectation starting from x of exponential f xs minus 0s v xr dr, that this is constant in time, in s, and equal to fx. Right? So if I prove that this is constant in s, okay, I get exactly what I want, because at time 0, this is fx, exponential fx. Okay? So this is what I have to prove. But now if you look at this expression, you recall that actually this is, you can understand this as the exponential 0 to s of the function minus v xr dr exponential f xt. So this is what we called p t ps of the semigroup associated to minus v computed at the function exponential f at point x. Okay, so this was the definition of my semigroup P. Well, here we have a minus sign, P minus V. And I want to show that this is constant, so I want to show that the time derivative of this is 0. So what's the time derivative of this expression? Well, this is semigroup, and we computed its derivative. The derivative was given by L plus V in our previous term. So here L minus V, because we have the function is minus V. And this is applied to exponential f. Right? Okay, but now we have to, what is L? So what is L minus V of f? This is L applied to f minus V applied to EF. And what is V? V is this function. Okay, so V is exponential minus f times L of exponential f. So V, it's exponential minus f times L of exponential f. Okay? V is exponential minus f times L of exponential f. So when you multiply that by exponential f, these terms cancel. What remains is L exponential f, which is that. So indeed, this derivative is 0, which proves our claim. Okay? So these are the exponential martingales in the context of Markov chains. Okay? So these are the general observations. Now we will apply that to the exclusion process. So now I can start considering the exclusion process. So I'll take the symmetric exclusion process. Okay. The argument for the exclusion process with rates, it's very similar. So let me concentrate on the simplest model, which is the symmetric exclusion process. So the generator recall it's given by x, and here I have f sigma x plus e of eta minus f of eta. So this is the process. And what did we do? We started with an initial condition, so that let's say that we fixed a profile. We started the process from this, let's say, Bernoulli product measure. And we consider the measure, let me call that maybe Q. This is the measure on D 0T M. So M, it's the space of the positive measures with total mass bounded by 1. And what we prove is that this measure converge to a measure which is concentrated on a solution. So this measure Q, it's the measure which is concentrated on the solution of the heat equation with initial condition given by the initial condition we started from. Okay, so this is a measure which is concentrated on one deterministic trajectory, and this deterministic trajectory is the solution of the heat equation. So this is what we prove, the law of large numbers. Okay. So that is to say that if you take a function f, which is, so these are probability measures which are defined in this space. So if you take a function f, which is defined in this space, and takes value in R, which is continuous and bounded, then the expectation of f with respect to q and the expectation of this function will converge to the expectation under this measure, but this measure is concentrated on one trajectory, so this is just equal to f of u, of the trajectory u. Okay? So what we proved is that this sequence of measure is weakly converging to this one, which means that for any continuous bounded function, the expectations converge. But since q is concentrated on one trajectory, the expectation of f with respect to q is just the value of f at this trajectory u. Okay? So one example of continuous functions in this will be, so remember here it's a trajectory, pi. So pi, it's an element of this space. So pi, it's a trajectory, so for each t, it's a measure. Could be, for instance, the time integral of t of pi t, some continuous function. So that's an example of a bounded continuous function. Right? So this is what we proved. And now we want to address the question of large deviations. So I will take a set, let's say, K, which is a subset of set of trajectories, which is closed or compact. Actually, I will prove it only for compact. But I show you how to go from compact to closed sets. And I want to estimate what is the probability that pi belongs to this compact set A. Right, so this is what I would like to prove. It's that if I take the log of this probability, and I take 1 over n, and I take the limit sup of that this will be bounded by minus the infimum over all p pi in k of a certain function of pi. So this is the upper bound we would like to prove. And, okay. So I'll just apply the strategy we developed yesterday for IID. So what was the strategy? Well, the strategy was take an exponential martingale, which is a function of pi. But the exponential martingale that we had yesterday was a function of x and bar. So construct an exponential martingale, which is a function of pi, and then follow the strategy. So we have seen here we have seen that if I take any function f, then the exponential of f xt minus f x0 minus 0t exponential minus fx L exponential fxs, the s, that this is a martingale. Okay? So in our case, xt, it's my process eta t. or pi t. Maybe let me write it eta t. We have seen that there is a one-to-one correspondence between eta and pi. If you give me a configuration, I can construct a measure, and if you tell me what is the measure, I can recover the configuration with n fixed. Then, fine. So what is f? We will choose. Well, we want a function of the empirical measure, and we have a bunch of functions of the empirical measure. We'll take f of pi as you take a test function g, and you integrate with respect to pi. So that gives you a function of the empirical measure, which is bounded. And so this is the function which we will insert here. So I'll take this function f. So remember, what is this? This is 1 over n x gx eta x. Okay? So I'll take f to be this function, and actually I will multiply that by n. This will be my function. So this is playing the role of my x n bar, right? And then I'm multiplying by n, I'm getting Sn. So this is the role of Sn. Fine? So let me sketch the strategy, and then let's try to apply it. So the strategy is fix a function g, which is smooth. So let's say C2 of t, and define the martingale, exponential martingale, exponential. So I'm taking this object here. So this is pi n t g minus pi n 0 g minus 0 t. Then I have to compute exponential minus, and I'm multiplying that by n, say. So here there's n. L applied to this function, ds. And remember that my generator is speed up by n squared, so there is an n squared here, which I will put here. Okay? So this is my martingale. So this is a martingale, we know. And therefore, what I will do is, okay, let me write Qn to represent this measure. I want Qn of pi n in k. So what did we do when proving the upper bound? Well, we wrote this as an expectation of Qn of the indicator that pi n is in k. And then we simply inserted the martingale 1 over the martingale. And if 1 over the martingale, or the martingale, can be written as a function h of pi, or exponential h of pi, we are in business, because we will bound that. We will bound this 1 over m, which is the exponential of pi, by the exponential of the supremum for pi in the set k of h of pi. Then this is now a number, gets out from the expectation. This is bounded by 1. This is positive and has expectation equal to 1. So I'll get this bound. Okay? So if we are able to show that this martingale is a function of pi, we are in business. We can just apply this strategy I presented. So this term here, it's a function of pi. This term, it's a function of pi. And then there is this term, which I need to compute. Okay? If this term, by chance, it's a function of pi, then I'm happy because I can just apply exactly the same strategy used yesterday in order to prove the upper bound. Okay? So this is the idea. So let's compute this exponential term, this integral term. So this integral, it's exponential minus n by g L of exponential n by g. Right? Fine. So L, I know what it is. It's the sum of my function computed at the configuration sigma x plus e of eta minus exponential n by g, computed at eta. And this is multiplied by this exponential minus. Right? So this is what it is. Now, I can insert this expression, this exponential, inside the sum. And you see here, I will get 1. And here I will get this exponential with minus here term. So what I have is that this is equal to the sum of exponential n by g computed at sigma x plus e of eta minus n by g computed at eta, and this minus 1. When I multiply both terms by this exponential. So we have to compute this difference. So let's compute it. So we have to recall that this n times pi, it's this expression. N times this integral is that. So I have a sum over y of gy, eta y, but it's not eta y, it's sigma x plus e eta. So sigma x plus e eta computed at y. And this minus now the same thing. So this is a sum over y of gy times this difference. Right? But we know that sigma x plus e eta at y, it's equal to eta y if y is different from x and x plus e. So I just have to compute this at y equal to x and y. So at y equal to x, this is gx. And here we get this configuration at x, but this configuration at x, it's eta at x plus e. Minus eta x. And now at y equal to x plus e, this is plus gx plus e. And now at x plus e, well, we are exchanging, so this is eta at x. And minus eta x plus e. So actually, if you remember, we did already this computation. And what we get is that this is equal to minus gx plus e minus gx, eta x plus e minus eta x. So this is this difference, and this is what appears here at the exponential. So let me go back to this term. Let me call that star. And what we are showing is that star, it's equal, I have a sum over x. And then the exponential of this term minus 1. Right? So mind that this term, the integral of g with respect to pi, it's a term of order 1. When I multiply that, I have a term of order n. Okay? So this term, it's of order n. While this one, well, mind that there is an n square in front. So let me put the n square now, just to get all the n's correct. So in principle, this term, it's a term of n cube. Okay? But this difference, it's order 1 over n. So this difference, it's 1 over n. Okay? So this makes, well, again, 1 over n, but it's still n squared. And I need a term of order n, not n squared. So what we need to do is, well, we need to expand this exponential and check if we can make that of order n. So let's expand this exponential. So the first order term will give me minus gk plus 1 plus e minus gx, eta x plus e minus eta x. So this is the order 1 term. The 0 term, they cancel. Then I have a plus 1/2 of the square. And mind that this term, it's order 1 over n. I get here a square, so 1 over n squared. That will cancel this n squared. I'll have a sum. So this term, it's already of order n. So I don't need to go into further the expansion because I will get lower order terms. So I can stop my expansion here. So for this term, we can integrate by parts. This term, in principle, I have here 1 over n, but it's n squared, but I can perform a second integration by parts here. Okay. So let me integrate it by parts to make appearing the discrete Laplacian of g. So I will write that as eta x. So here I'm replacing x plus e by x. So this gets me gx minus gx minus e, and I have a minus sign. And then I have minus these terms, so minus gx plus e plus gx. So this is my first term. And the second term, I will just introduce the n squared inside and replace this discrete gradient by the continuous one. So plus 1 over 2 x. Okay, maybe let me first leave the discrete gradient. And so what I get at the end with this minus here, I get the discrete. Okay, so let me continue this computation here. So here I'm inserting the minus sign here to get that this is the discrete Laplacian of g computed at x, eta x, and then plus 1/2 of the discrete gradient of g square times this function eta x plus e minus eta x squared. Okay, so this is what we get. So this is what we get from this computation, and there is an error, but the error here it's 1 over n with this plus order 1. Okay. So now let's replace in this formula for the martingale what we obtained. If I had only the first line, I would be very happy because the first line can be written as n times the empirical measure, which is integrating the second derivative of g. So it's a function of the empirical measure, the first line. However, the second is not. Okay? The second, this expression is not a function of the empirical measure, and therefore, well, I cannot apply it immediately what I wanted. Because here I appear the function which is not a function of the empirical measure. So if I develop this square, I'll get eta at x plus e square, but since eta it's either 0 or 1, the square is equal to its value, plus eta x, but I get minus 2 eta x plus e. And this function is not a function. So we are in trouble. And here the idea is exactly the one that we used in order to prove the hydrodynamical limit. We want to replace this function average with respect to that one by a function of the empirical measure. So what we will do is that we will write this as 1 over 2 x g prime at x square. And here this function, let me call this function h. So h of eta will be the function eta e minus eta 0 square. So what I'm having here is the translation of this function by x. And so what was the argument? Take the expectation of this function with respect to a Bernoulli. So if I take the expectation of this function with respect to the Bernoulli, what I get is alpha plus alpha, so 2 alpha minus 2 alpha square. So this is 2 alpha 1 minus alpha. Okay. Let me call this function h hat of alpha. And what I want to do is to replace this function, to compare this function with h hat of eta epsilon n at x, where eta epsilon n at x is the average of particles in a box of size epsilon around x. You recall that notation? Okay, so eta epsilon n x, it's 1 over 2 epsilon n plus 1, the sum for y minus x less than epsilon of eta y. And what we did when proving the hydrodynamical limit was showing that this difference is small. Right? So, let me rewrite the martingale, and now let's try to think what we can do. So the martingale that I introduced, it's the exponential. Let me put an n here. This is pi n t g minus pi n 0 g, and then minus 0 t. I have a pi n s Laplacian g ds. This one is very nice, but then I have minus the 0t 1 over n sum in x of gradient g at x square times tau x h of eta s ds. So this is n plus. So since I'm putting the plus an error which is uniformly bounded by 1 over n. Okay? Do you agree with that formula? Okay, so this is a computation. So this is computation we did. Where the function h of eta, it's eta 0 minus eta e square. And now, I don't know if I introduced this notation, but let me introduce it here. This is the expectation of h, which is, in our case, equal to 2 times alpha 1 minus alpha. Fine. And well, we have again to close the equation. We have an expression which is not a function of the empirical measure, and we want to transform it into a function of the empirical measure so that we can apply the strategy I presented yesterday. So questions? So now I will consider set B, which depends on epsilon, delta, and G, which is the set of all configurations eta or S, so all trajectories, such that so I want to compare this with H hat. So this is the space of trajectories for which this integral from 0 to t of 1 over n. Okay. Maybe I'll write it below to have space, such that the integral from 0 to t of 1 over n, the sum of exactly what's written there. So this is gradient gx square of tau xh of eta s minus h hat of eta epsilon n s at x ds, that this is less or equal than delta. Okay, so this depends on this delta, on this epsilon, and on the function g. Okay. And what I'm saying is that on this set, this martingale, it's equal. Let's say, let me call that line 1, this line 2. So my martingale is equal to the exponential of n times line 1 plus line 2 plus the integral from 0 to t of 1 over n x gradient g x square h hat eta epsilon n xs ds let's say it's bounded, or okay, now it's equal to then I have exponential n order 1 over n plus order delta. Okay, because by replacing this expression with h hat, I'm paying delta. Okay? So this martingale is bounded above by constant times delta and bounded below by minus constant times delta. This is what the meaning of this identity. Okay? And now I'm happy because this is a function of the empirical measure. Now I can apply my strategy. But the problem is that I introduced this set, epsilon, b, epsilon, delta, and so on. So what I will do is So let me go back to my proof. I have here introduced what I want to estimate. It's the probability that pi n belongs to k. Oh, fine. I know that in this set, everything is fine. So let me intersect my compact with this set and bound. So I'll intersect this with the set. I'm b epsilon delta g plus q n b epsilon delta g complement. Okay. Then use that 1 over n. So this implies that the limit sup of 1 over n log qn of pi n in k, it's bounded by the maximum of these two limits. So the first limit is just 1 over n log of this expression, which I won't write, and then the limit sup in n of 1 over n log qn of this set, the complement of this set. And by the same reason, if I can show that this is converged to minus infinity, then I'm fine. Because, well, if this converges to minus infinity, I can ignore it. And here, since I'm in this set, I will be able to replace everything here by a function. Okay, I'll be able to introduce the martingale, to write the martingale as a function of the empirical measure, and to apply my strategy. So there are two steps. I have to show that this limit, the limit of this set, as n goes to infinity and then epsilon to 0 goes to minus infinity, and then consider that expression. Right? So I will address this problem, and then I'll go back to that one. Fine? So I will erase everything, just keep what is my set, and prove that this limit goes to minus infinity when I send n and then epsilon. And once, after doing that, I'll come back to the second term. Okay? Okay, so maybe it's a good time to stop, because that will take me more than half an hour, and it's better that you see everything on one class. Okay, so we stop here and we continue on Tuesday.